we discuss about equations of order 1. The standard form of an equation of order 1 is m of xy dx plus n of xy dy equal to 0. So if the variables are x and y, we write the standard form of the differential equation of order 1 as m of xy dx plus n of xy dy equal to 0. So m is a function of x and y, and n is also a function of x and y. But there are some equations simple enough in such a way that you can rewrite an equation where the coefficient of dx is a pure function of x and the coefficient of dy is a pure function of y. No? So if you are given this equation and you can turn this into an equation wherein you have a pure function of x, dx, plus a pure function of y, dy, equal to 0 results, then we say that the variables are separable. So the only thing we have to do here is to integrate everything to arrive at the solution of the given differential equation. Okay, so let us write it down. If 1 can be written in the form let me use f of x dx plus g of y dy equal to 0, then we say that the variables are separable. So to find the general solution, of the differential equation 1 is to integrate both sides of, let us call this as equation 2. Right? So it's as simple as that. We rewrite the given differential equation in a way where the coefficient of dx is a pure function of x and the coefficient of dy is a pure function of y. So let us take on our first example. We solve dy dx equal to e raised to x plus y. So how do we do this? Let us cross multiply. Hence we have dy equal to e to the x plus y dx, or e raised to x plus y dx minus dy equal to 0. What do we see here? E raised to x plus y, and there's a way of separating the x and the y. That is equivalent to e raised to x times e raised to y dx minus dy equal to 0. So in this way, we can see that ey is an unwanted coefficient of dx. No? So we want to get rid of e to the y, and it's simple. We just divide both sides by e raised to y. So doing so, we'll be getting e to the x dx minus dy over e to the y, or e to the negative y dy equal to 0. So we can see now that the coefficient of dx is a pure function of x, and the coefficient of dy is a pure function of y. So we just evaluate the integral of both sides, and what do we get? E raised to x minus the integral of e to the negative y dy is negative e to the negative y equal to c. Okay, where c is an arbitrary constant. So the integral of of 0 is constant, as the derivative of a constant is 0. So this is the same as e to the x plus 1 over e to the y equal to c. No? We can write this as e to the x plus y plus 1 equal to c e to the, let me see, e to the y. So multiply everything by e to the y. E to the x, e to the y is e to the x plus y, and 1 over e to the y times e to the y is of course 1, c e to the y. So you can write your final answer in the form e to the x plus e to the minus y equal to c, or in the form e to the x plus y plus 1 equal to c e to the y. So both will be acceptable. Okay? Now, say you want to find, no? Find a particular solution. To find a particular solution is to get a specific value of c, no? For a given pair of coordinates x, y. Remember, this expression represents a family of curves. So, say we represent this family, okay, by these curves, all right? Then we want to find a specific member of the family. Say the one passing through the point 1, 1. Okay, 1, 1. So what we do is we simply substitute these coordinates, 1 for x and 1 for y, and we solve for c. Once we have determined the value of c, we plug it in to the equation to get the particular solution, or the equation of that member passing through the point 1, 1. So find a particular solution for x equal to 1, y equal to 1. So we have e to the x plus e to the minus y equal to c, e raised to 1 plus e raised to negative 1 equal to c. Okay? So your c is what? E plus 1 over e. Alright? Or e squared plus 1 over e. So just substitute this value to c, and you have the equation, the particular solution, e to the x plus e to the minus y equal to e squared plus 1 all over e. You can multiply everything by e to the x plus 1 plus e raised to 1 minus y equal to e squared plus 1. Okay? So that is the particular solution. Let us say we want to find the particular solution where x is 0 and y is 0. Find the particular solution for x0 and y0. So e to the x plus e to the minus y equal to c. E to the 0 plus e to the negative 0 is 0. C. But what is e to the 0? 1 plus 1 equal to c. So c is equal to 2. So the equation of that member passing through that point, the origin, will be e to the x plus e to the minus y equal to 2. Okay? So the general solution will involve an arbitrary constant c, and a particular solution will give you a specific equation of the family. Let us solve another one. Let us solve x cosine y dx plus x squared plus 4 sine y dy equal to 0. So let us examine the coefficients. X cosine y is unwanted, cosine y in particular. X squared plus 4 sine y dy, x squared plus 4 is unwanted as far as dy is concerned. So, to solve this, this problem is to work on the coefficients by dividing both sides by the unwanted coefficients cosine y and x squared plus 4. Okay, so what will be the result? X cosine y dx over cosine y x squared plus 4 will give me x dx all over cosine y x squared plus 4 plus x squared plus 4 quantity sine y divided by cosine y x squared plus 4 will give me sine y over cosine y dy equal to 0. Okay, so we can see that the coefficient of the x is a pure function of x. Oops, sorry, there should be no y there. There should be no more cosine y because we have multiplied or divided by cosine y. Okay. So the coefficient of the x is a pure function of x. The coefficient of dy is a pure function of y. We proceed? No, not yet. We can simplify this. So x dx over x squared plus 4 plus, of course, sine y over cosine y is tangent y dy equal to 0. We integrate x dx over x squared plus 4 is, of course, 1/2 ln of x squared plus 4 plus the integral tangent y dy is ln of the absolute value of secant y equal to, okay, so the constancy here can be written in the form ln of c. Why am I doing that? So later you will see the rationale why I'm writing the constant as ln c and not just c. And then I can also divide it by 2. It will still be a constant. Why am I doing that? So that when I multiply everything by 2, I'll be getting, so multiply by 2, I'll be getting ln of x squared plus 4 plus 2 ln of absolute value of secant y equal to ln of c. As you can see, there is no more fraction involved. There is no more fraction involved. And then I can write 2 ln secant y as what? Ln of secant squared y equal to ln of c. Okay? And then I can combine these two ln's as one ln of x squared plus 4 secant squared y equal to ln of c. Alright? And I exponentiate both sides to get rid of ln. So exponentiate both sides. Doing so, we'll be getting e to the ln. And what is e to the ln of x? That is x, right? Because e and ln are inverse functions. Alright? So e raised to ln of x squared plus 4 secant squared y will just give me x squared plus 4 quantity secant squared y equal to ln of c. E to the ln of c will be equal to c. Okay? Another way of writing our answer is x squared plus 4 equal to c cosine squared y. How is that? Secant squared y is 1 over cosine y. And then we multiply both sides by cosine squared y, and this is what we will get. Alright? So let us have another one. This will be the third example. We solve xy cubed dx plus e raised to x squared dy equal to 0. So y cubed is not a desirable coefficient for dx, no? And e raised to x squared likewise is not a good coefficient for dy. So we divide by y cubed e to the x squared, and what do we get? X over e raised to x squared dx plus dy over y cubed equal to 0. And so we get x e raised to negative x squared dx plus y to the negative 3 dy equal to 0. So our equation is perfect now, no? The coefficient of dx is a function of x, and the coefficient of dy is a function of y. We proceed. So what is the integral of x e raised to negative x squared? The derivative of negative x squared with respect to x is negative 2x. So that will be negative 1/2 of e to the negative x squared. Plus y to the negative 3 becomes y to the negative 2 over negative 2 equal to, since they are all negative, why not use negative c over 2? Okay? So multiply everything by what? Multiply by negative 2. And what do we get? E raised to negative x squared plus y to the negative 2 equal to c. Okay? If you want, we can write this as 1 over e raised to x squared plus 1 over y squared equal to c. So multiply everything by e to the x squared, y squared will get e to the x squared plus y squared equal to c, y squared e to the x squared. We take on another one. Say x cosine squared y dx plus tangent y dy equal to 0. So we divide by cosine squared y, and no, let tangent y remain as is. No? Just cosine squared y. So divide by cosine squared y. We'll be getting x dx plus tangent y over cosine squared y dy equal to 0. 1 over cosine squared y. No? 1 over cosine squared y is equivalent to secant squared. So we can write this as tangent y secant squared y dy. Why am I doing that? Because secant squared y is related to tangent of y. The derivative of tangent y is secant squared y. So for this part, we can use the power formula. So to integrate the second integral is to apply the power formula. By the way, this is equal to 0. So what do we get? X dx is, of course, x squared over 2. And apply the power formula for tangent y secant squared y dy, where our u is tangent y and du is secant squared y dy. It will give us tangent squared y over 2, and you probably know what will be the form of the constant. No? That will be c over 2. So multiplying everything by 2, we'll get x squared plus tangent squared y equal to c. Next one. Let's say x dx minus the square root of a squared minus x squared dy equal to 0. It is clear that we do not want square root of a squared minus x squared to be part of dy, so we divide by square root of a squared minus x squared. That will be x over the square root of a squared minus x squared dy. Oh, sorry, that should be dx minus dy equal to 0. We now integrate. So what do we use here? We apply the power formula. So the derivative of a squared minus x squared is what? Negative 2x dx, and the differential. So it locks negative 2. Negative 1 half, power formula, a squared minus x squared, negative 1 half plus 1 is positive 1 half over 1 half. Okay? Then minus the integral of dy is y. Again, you should know that the constant will take the form negative c, because the terms we have at the left side are both negative, so we write our constant as negative c. And that way we will come up with a nicer answer, no? So 1 half here will cancel, of course. We have negative square root of a squared minus x squared minus y equal to negative c, or equivalently square root of a squared minus x squared plus y equal to c. Okay? So let us have another one. Last example. Y ln x ln y dx plus dy equal to 0. Okay. So y ln y is unwanted. Ln x dx plus dy over y ln of y equal to 0. To integrate, we know that the integral of ln x dx is x ln x minus x using integration by parts. No? If you still recall your technique of integration, using integration by parts, ln x dx is x ln x minus x plus. How about this one? We can take on ln of y as our u, and your du will be dy over y. So this takes the form what? Du over u. No? dy over y is dy over y is your du, and ln of y is your u. And we know that the integral of du over u is ln absolute value of u, which is ln of y equal to c. Okay? So what do we have now? X ln x, x ln x plus ln of y equal to c plus x. I just transpose negative x to the other side so that it will look nicer. So that's it. The only thing we have to do, given the differential equation of order 1 m of xy dx in the standard form plus n xy dy equal to 0, if we can transform this into fx dx plus g of y dy equal to 0, then the variables are separable. No? And we can easily get the solution by just evaluating both sides of the equation. Okay?